Hello, everyone. My name is Edoardo Farina. I am a particle physicist and I work at CERN in Geneva. So I decided to join the Advanced Data Science IBM specialization to widen my knowledge in data science field, especially to know about the framework available, in particular Apache Spark and machine learning. So today I will briefly present you my Capstone project done for the final IBM specialization assessment, focusing on the analysis, modeling, and forecast of extreme weather events in Basel, Switzerland. So a little bit of general introduction. So climate change and temperature increase is trend topic every summer. So in the bottom left plot, you can see as measured by Meteo Suisse, the increase of temperature since 1760 in Switzerland. So you can see that we have had an increase of temperature of about 3 degrees. So of course, the temperature increase does not only affect glacier and the melting of the ice, but it has a very important and immediate effect on the climate. One of these is we are already facing is the increase of violent extreme events such as heat waves, very long dry periods, or floods. So this project aims at analyze the temperature, pressure, humidity, and other variables in the city of Basel in the last 35 years to also evaluate the increase of such events, if any, and then to provide a machine learning framework which able to reproduce the past trend and to forecast the future, possibly. So our data source are the climate measurements performed in Basel, and that can be downloaded from the meteoblue.com website for free, at least for the city of Basel. It provides CSV or Excel file that the user will choose the preferred one, and it will allow to download all the relevant information such as precipitation, temperature, humidity, wind speed and direction, and so on. So, and the data, several data sets can be chosen. The data is provided hourly, and in our case, the data starting since 1985 has been downloaded and exported as CSV file into independent data sets for a comprehensive data set size of a few hundred megabytes. So concerning the project structure, it's based on Jupyter notebooks, several of them. So the first one concerns the data extraction, some preliminary analysis and data transformation, and very preliminary data visualization. So in the second notebook, we focus mostly on the data analysis and visualization and feature engineering, especially concerning the what we call the extreme weather events. In the third notebook, I will focus on the machine learning definition and the training, while in the fourth, we will do the model evaluation. And finally, we will, in the fifth notebook, we will provide another model for different data, again, train, evaluated, and also used for making some predictions. So first notebook concerns, as I said, to extract, transform, and load of data. In the slide, you can see a little bit of a schema of what happens there. So first, data is loaded, and I profit of the Apache Spark data frame features to handle the data. Apache Spark allows very versatile, flexible, and performant data handling. So then the data is cleaned, namely removal of missing information, as for example null or so. Data is also are also ordered by date, by time, to have a proper sequence. And most important, the data are reduced in size by grouping, for example, by year or by month, in order to have a more comfortable dataset size and by keeping the relevant information. And finally, the data sets can be saved in different ways, depending on where the notebook, the Jupyter notebook is run and the environment where it is run, or as a CSV file, or for example, to an object storage if run on IBM Watson Studio. Very preliminary data visualization is shown here. So in the top plot, you can see the temperature per each hour since 1984, while in the bottom plot, you can see the wind speed, again, per hour since 1984. So this data do not provide much meaningful information, but this is the very raw data we downloaded from the website. So our output dataset is the structure of the output dataset is shown here. So our data frame, you can see the schema in the bottom of the slide. So we are basically collecting the maximum, minimum, and average temperature per day. The same for the wind, and the same for the rain, and the same for the humidity, for a comprehensive 36.54 years of data. So for each day. Concerning the data analysis, so you can definitely find more in the Jupyter notebook, which you find on the GitHub repository. I will just focus on two very interesting, in my opinion, elements. So you can see on the top plot the maximum rain intensity per year as a function of the years since 1984, while in the bottom plot you can see the total amount of rain fallen in arbitrary units. It's not normalized to the hours, but it doesn't really matter, as a function of the time. So what we can learn from these two plots is that the amount of rain which is fallen, it's decreasing, as you can see from the bottom plot, but the events where a lot of rain is falling, so extremely violent storms, are actually increasing. And just to remind you that 2021 is not yet complete. So in few words, it rains less, but it rains more violently. Concerning the temperature, you can see in the top plot the maximum temperature reached per day as a function of days since 1984. While on the bottom plot, you can see the average maximum temperature per year and the average temperature, again, per year since 1984 up to today. And unfortunately, you can see that we can confirm the meteor Swiss data. We can actually see an increase of temperature since 1984, and the trend seems to be quite clear. Again, the 2021 point doesn't need to be taken into account, since 2021 is not yet finished, and actually summer is yet to come. So as I was saying, one of the first and immediate problem we will face is from climate change is the increase of violent events, heat waves, storms, floods, and so on. So here, in this case, I decided to define a threshold in terms of maximum temperature reached per day and precipitations, such as to count the number of days which fall above this threshold. You may argue that these thresholds are not the correct one, or maybe can be modified. Okay, but I think nobody can argue with the results we will show in the bottom of the slide. So here you can see the number of days which are fallen above our threshold. And as you can see, the number of days increased of almost a factor 2 since 1984. This means that the hot or rainy or actually heavy rain days increase of almost factor 2 since 1984. So this is actually what we were worried about. So the extreme events are indeed increasing. Let's move now to the machine learning part. So we decided to implement a recurrent neural network based on LSTMs. So here you can see again a plot you have seen already before, the maximum daily temperature as a function of the day since 1984. So here it's divided into training and test dataset. I've used the incomplete data from 2021 as our dataset. It would be probably good to increase a bit. A zoom plot part of the top plot is shown in the bottom slide, in the bottom plot, where basically the 2019, 2020, 21 data are shown. So concerning the internal model structure, this is based on several layers of LSTMs of different size. The activation function is TANH, and we are using the recurrent activation SMOID, plus a dense output layer in the end. So we use the Adam as optimizer, and the loss function is the mean square error. You can actually, you see on the left of the slide, the structure of an LSTM is out of scope of this presentation to show how this works. So after training the data on my local machine for quite some time, I was able to actually compare the test dataset with my predictions. So predictions are done on previously unseen data. So you can see here the comparison between the two. The x-axis are basically days since January 2021. And actually, you can see that the root mean square error is about 4 for a loss function for a loss of about 26.6%. So this is quite a reasonably good result. I'm quite happy with it, and it seems that the model is able to predict quite well previously unseen data. So the second model is actually focusing on monthly maximum temperature. So in this case, we are not taking into account daily temperature, but monthly temperature in order to reduce a bit the dataset size. So in this case, you can see again the maximum daily temperature, in this case, it's a zoom plot starting from 2014 up to today. So in this case, training and test dataset have been splitted, considering training whatever happens before 2020. So 2020 and 2021 have been considered as a test dataset. Okay, good. So the model is very similar to the one we have seen before. It's always composed of few LSTM layers plus a dense layer in the end. So again, after training the model, we could get a root mean square error of about 25 with a loss of 14%. And in the bottom plot, you can actually see as a function of the month starting from July 2020, the comparison between the real test data and the predicted one. And again, you can see that the agreement is quite good, and we can say that the model works quite well on previously unseen data. The model does also provide the possibility of predicting a few months in future. So this is what is shown in this plot here. You can see the blue line is the forecast for the month starting from August 2021 up to January 2022. So in conclusion, we have performed the analysis of the principal meteorological variables since 1984 in the city of Basel. So unfortunately, we have observed a clear trend in the temperature, which is increasing over time, and precipitation. So it rains less, but it rains more violently. We have seen that given our definition of say, extreme events, we have seen that there is an increase of almost factor 2 in extreme days since 1984. And unfortunately, this trend does not seem to stop here. It will continue in future. We have seen that we have developed 2 LSTM based models in order to model and predict our data In our case, we were using the daily maximum temperature. In the second case, the monthly maximum temperature. And both models seem to work quite well on previously unseen data. And we also provide some forecast using the second model for the next 6 months. Of course, still a way to go. Further optimization can be foreseen, especially for concerning the machine learning model, concerning, for example, parameters tuning, longer training, trying different activation functions, and so on. So with this, I conclude my presentation, and I really very much thank you for your attention, and goodbye. Thanks a lot.